Lesson 2.4. Calculation of flat trusses using the section method from the book Mechanical Systems Calculations of the Marine Facilities. Calculation of flat trusses using the section method. Actually, we will not consider not only section method, but the cutting knot method as well. So usually we have two methods of determination of the forces acting on the truss mechanical elements. Truss mechanical elements are bars or rods. So we'll consider not only trusses section method calculation of forces, but as well the determination of forces by the cutting knot method. And I just want to indicate first that the issue of calculation of trusses is the determination of the support reactions of acting on truss, besides of the external load, and as well the issue of the calculation of the trusses is the determination of the forces the acting in the rods in the trusses of tension forces and compression. The assumptions made when calculation forces in truss elements are the external forces are applied only at the truss nodes. If we have in any case any other options of the acting external loads on the truss, we have first to determine the concentrated force equivalent to other than applied to the nodes, but we have for determine first the concentrated force acting to the nodes to calculate the truss elements in the next. When calculating the truss, one can neglect the mass of the rods and the weight distributed over the rod. As well, if we have the mass of any of mechanical element of truss, it's the rod hinged. So first we have to transform this into the knot forces acting on the knots, load forces in the knots. And see the truss knots are ideal hinges, so there are no gaps in the hinges. So rings and shafts in the hinges are with not gaps. And one can neglect the friction of the hinges. Besides, for static definable trusses, we have the relationship between the number of rods and the number of knots. If we say rods by the sign indicate by the sign S and the knots indicate by the sign U, the proportion is a number of rods minus 3 equal to product 2 by brackets, in brackets, number of the knots minus 3. So this is an example of the truss. Static definable truss, we can consider the composition of the not changeable triangular discs consisting each of 3 rods of truss connected in the hinges. Here on the sample, a triangular disc of as a part of the truss is ABC. Another, we can put another triangular discs to the previous one, and we can next have the truss. Calculation methods of flat trusses, I told that it can be usually the method of cutting knots, and we cut definite knot like here on the draft 2.4.2b. On the right, we have C cut knot from the truss. Consider the left on 2.4.2a, and we next after cut knot from this truss. Next, we consider the preconditions of balance of the knot C, and next we can find the forces acting in the bars, in the rods of this truss. Or we can select a definite part, not just only one knot, but definite part of truss. This is section method. A section we consider the equilibrium conditions for the cut section of the truss. So this is section method on the draft 2.4.2b on the right. For example, we consider the balance equations around the reference point B. It can be the reference point of any coordinate system, like y, x, for example, or the point of determination of the rotation moment around that. For the separate one rod in the truss, we do not consider the bending moment, but for disks consistent of rods, we can consider the rotation moments caused by acting forces in the sected in the cut rods when we do, for example, the section method. Besides, it's very convenient to introduce the concept of zero rods. Sometimes watching on the specified truss, we can define the rods with zero efforts. Rods with zero efforts. Zero rods. Zero rods we can consider by the attributes. The first, for example, if an unloaded no two rods that do not lie on the same line converge, then both the rods are zero. So, for example, here on the draft 2.4.3a, we have the two rods connected on the hinge. The two rods do not lie on the same straight line, and the hinge, the node of the rod of the truss, is not under any force external, not loaded. So these two rods are zero rods. If three rods converge in unloaded node, two of which lie on the same straight line, then the third rod not lying on the straight line is zero. So as a sample on the draft 2.4.3b, we have the connection of three rods in the hinge here. And this third rod is not on the same straight line as the previous two. So this third rod is zero. Do not have the forces inside. And attribute 3, if two rods they do not lie on the same straight line converge in a loaded node, and the external load is directed along one of the nodes, and the second rod is zero. Yeah, if here we have the, as on the left A, almost the same on C, but the node is loaded by the force. So if this force is on the same straight line as one of rods, for example, here we can see the rod on the same straight line with the force. So the rest rod is zero, have zero tension in the rod. Besides, we would consider the exercise as an example. We have to find the zero bars for given truss. This is a truss. We have one force. Bars is statically definable, so it's supported by the fixed hinge and the sliding hinge B, A fixed, B sliding. The force applied to the node G. Okay, which rods are zero rods? We can start on the right, from the right to the left. We have, if node C, the hinge is not under the load, that is 10 and 11 zero rods. Is 11 0, the 8 is 0 because they lie on the straight line. The 9 rod is 0 because on the same line. Then 9 is 0 because two other rods is 0. Not this node is not under the load. Consequently, as 9 and 10 rod is 0, the node E not under the load. The rod 7 and 6 zeros. Next, we can find that if zeros, the H is 0, 5, and 4, 0. So only loaded rods are 1, 2, 3. 1, 2, 3. And 4, 5, 6, 7, 8, 10, 8, 9, 10, and 11 are no zero rods. Are zero rods, excuse me. Exercise second, determine the forces in the bars for a given external force. So this is assigned the truss loaded by the force F acting to the node C from right to left, and the force is assigned as 5 kilonewton. But the sizes of this truss is not assigned, are not assigned sizes, but we just know that the segments equal A. So we can use the methods of for determination of the forces acting on the rods by the cutting knots and the method of sections. Here we indicate where we can cut the knots. We can cut the knots, for example, 6, 7, 8, and consider the balance of the rest part of the mechanical system and find the forces in the rods 6, 7, 8. After that, we can do the section here on the truss. We can find the forces in 1, 2, 4, considering really the assumptions of the balance for the rest part of section. We can find the forces in the rods 1, 2, 4. These forces are substitute of the action of the rod when we consider the equivalence, not equivalence, but the balance or equilibrium of the rest part of the section. Okay, but to do that, actually, first it's more reasonable to determine the forces of the support reactions in A and B. In A, with a fixed hinge, we have the projections on two axes, X and Y. On the X and Y axis, the support reaction, the hinge A, node A, and the sliding hinge X in the node B. We can find only one vertical reaction, RB, or the same as this is YB. And please consider the balance equation for the total truss relative for integral truss relative the first the projections of all forces on the acting on the integral truss on the axis X abscissa. So axis X, horizontal axis, and on the integral truss we can consider only two forces in the horizontal direction, the force reaction XA and the force F. They are in opposite direction and acting parallel. So we have the projection of the reaction in the fixed hinge A here equal to the force and equal 5 kilonewton. After that, we can consider the balance equation relative to the points B and A of the integral truss. Relative to the point B, we have action of the projection of reaction in the support A on the axis Y. It acts counterclockwise with arm A, so, and we have the force acting counterclockwise with leg 2A, so we can determine that the YA is 10 kilonewton force. It's 10 kilonewton directed up clockwise. So we next consider the balance equation relative 0.8 for the integral truss, and two forces act RB and F, and next we have that considering the balance of rotating moments around, we have that RB is minus 10 kilonewton directed downwards. Okay, so we have the acting on this truss, the external force and the support actions XA, YA, RB. RB is exactly the same time the YB too. So we can cut knots and we can determine the forces acting in the cut knot. Okay, just for example, we will cut knot C to determine to consider the equilibrium equations of forces acting on the knot C, and this is why we can find the balance of point C on axis X and axis Y. We correlate the refer the coordinate system to this point C and direct the axis X on the left and axis Y downward, and the balance of the forces on the axis ordinate gives us the force in the bar H is 0, because the force load of force do not have the projection on the vertical axis, and that force in the 9 rod is minus F, equal minus 5 kilonewton, is a force in the 5 rod. After that, we can do the cutoff part, and we can find the balance. We can consider the balance of rotating moment relative to the point K. Relative to the point K, for example, point K we have here. We cut off this part, and we substitute the rods by the acting forces, and we have the projections of rotating moment around the point K of acting external force, and with the leg A, and the force S6 with the leg A2. Force F6 rotate the counterclockwise, we assume, but because we can find the negative side, but actually we can assume any direction of the force before the determination. Just only after that we have to correlate with the magnitude sign with sign of the assumed the axis. So force in the 6 rod relative point K. The force in the 7 rod do not cause the rotating moment, because the force in the bar 6 intersect the point of rotation K. So, and the force in the we got previously in the bar H equal to 0. So we have only force 6 and the loaded by the section and the load force F. And next we find that the force in the 6 rod of the truss is minus 5 kilonewton. After that, we consider the total of all forces on the abscissa axis X. Sorry, abscissa axis X. We consider force S7 projection with the angle 45 degree, because two sides of this rectangular segment, for angle segment of the truss is the same sizes, is of the same sizes. So the A and A, two legs, and the angle between the diagonal and the side is 45 degrees. So we consider that the balance equation, that the force and the acting force on the node C and the force in the 7 bar have to be in the balance, and the force in the 7 bar is division of the magnitude of the force F by cosine 45 degrees 5, product 5 by square root of 2. And the rotation around the point, the node D, around the node D, give us that the force in the H rod is equal to 0 that we got before. After that, we can consider the second section. Second section we had here in the lower part of the assigned truss. We have forces in the 5 node is A0, node is 0. Force in 6 node is minus 6, excuse me, minus 5 is equal to the same as the forces in the first rod. So these two rods, 6 and the first, are on the same line, and we have the force 5 is perpendicular to this line, so the force 5 is in the rod 5 is 0, and that's why the force in the rod 1 and rod 6 equal in the size, and of the opposite direction have to equal 5 minus 5 kilonewton. And next we can do the cut nodes. We can cut node E, and we can not B in the next. B is one of the support node. When we cut node E, we consider the projection of forces on the axis Y and axis X. And okay, so first we consider the second cutoff part for the balance equations of projection of forces on the x-axis, and we find that on this cutoff part only in horizontal direction only external load force acts, and the projection of force F2 as well, because other forces directed in the other forces in the section and external directed perpendicular to the axis X. So the force in the bar 2 S2 equal of minus force 5 due to the balance equation equal to minus magnitude of force signed external load F divided by cosine 45 degree. So minus 5 product minus 5 by square root of 2. After that, we can consider the equations of the rotation around the point A. We have forces acting on the cut part of the truss and the balance equation for this cut part of truss relative the node A. The total of rotating moments MA is that two forces S1 and F2 crosses the point MA, so the moments caused by forces F1 and F2 are equal to 0. So we have only moments of the force external load assigned and the force of the force and the moment of force in the sected rod 4. So this force rotate counterclockwise on behalf of the force F, and so is positive moment, and the force S4 rotate around the point A clockwise is negative moment. So finally we have that the force F4 is equal to 10 kilonewton because the lack of force F equal to A, and the lack of force S4 equal just only one is the other legs, and the force have to be twice bigger than the force loaded the truss. And we can as well consider the balance equation of the rotation of the cutoff part of the truss around the point K. We have external load, we have two loads S2 S4 crossed the point of rotation K, and only one force S1, which rotate the cutoff part of the truss besides of the external force F. So we consider these two. These two is positive moments rotating around the point K counterclockwise. So we have that the force in the rod 1 is of negative magnitude and equal to 5 kilonewton. The conditions of balance relative to the node B. Next we cut the last one node B, and considering the conditions of balance, we have the force S3 equal to 0 because it is 0 node, not 3 is 0. As we have two rods one rod and another one is supporting rod, and this rod 3 in the truss is perpendicular to these two, which are on the same straight line. So the projections on the axis ordinata y of forces acting in the fourth rod of the assigned truss and the direction we got before, RB, have to be equal to 0. And that's why having the RB equal to 5 got before. So the force S4 in the rod number 4 is equal RB minus 5 kilonewton. Questions and comments. The truss is a rigid structure consisting of straight rods connected at the ends using hinge joint. Yeah, just a difference with the frame. Frame is the mechanical system consisting of the rods and rigidly connected with not hinges. And the truss connected by hinge joints. We assume that hinges are ideal that hinges do not experience friction and not have the gaps in the hinges. The assumption made when calculating forces in truss elements and the calculation methods used. Assumption that the all load is applied only to the nodes and not on the rods themselves, and we neglect the weight, the mass of the weight of the rods of the truss. If we have the mass of rods within the of the assigned truss, considered truss, first we have to transform this action of the load or any other forces applied to the definite one element of the mechanical system, like a truss. We have transformed this to the equivalent loads acted on the nodes of truss. And next assumption made when calculating forces in truss elements, this we told is the ideal property of hinges with no gaps, with no friction. 0 rods of trusses, the forces in which are equal to 0. Usually we can have the attributes of rods which is of 0 force, with not loaded by the force, the rods. And what is attributes of rods? The geometric attributes of rods which are not under the force. If two rods connected in the hinge and this hinge is not under the load, the rods are 0. If only two rods connected in the hinge. If we have 3 rods connected in one node in one hinge, 3 rods of truss, and 2 of the rods are lying on the same straight line, so the third rod, the rest one, is 0 rod. And if we have 2 rods connected and not lying on the straight line and connected in the node, in one node, now in one hinge, and we have the external load applied to this hinge on the same line of one of the rods, so the rest of these 2 rods is 0. Finding support reactions using the balance equations for the complete truss. Yeah, we can consider if the truss is statically definable, so the we can find the support reaction considering the balance equations of all forces and directions loaded to the truss. And we can consider, for example, the rotation moments around the points of support of truss, of hinges of the support of truss. Finding forces in the rods by cutting of the nodes. Yeah, this is one of 2 general methods of finding the forces in the rods, the cutting out the nodes. We can sometimes consider it's comfortable to do the considering of definite nodes of the truss separate, and we consider next the equations of balance for this definite one node cut. And besides of that, we can use another method of determination of forces in the truss rods. We can do the sections cut. So we can not cut the rod, but the part of the mechanical system, the truss. We can cut, and we can consider the balance equation for this cut out part of the truss when we substitute the cut rods by the forces acting on these rods. Thank you.